Hello and welcome to the YouTube channel of AIWithVik. We are getting started in the area of matrices, and we will first understand what is the motivation behind matrices in AI. So at the heart of AI, everything like from images to text, everything resides in grid of numbers. So matrices are basically the language in which these numbers are organized, stored and transformed, right? So let's say for example this is an image here, which is again transformed as a matrix. As Basically an image consists of pixels, and in pixels the number varies from 0 to 255, right? So you can see that the image resides as a matrix here. Similarly, we can transform texts as matrices also. Each word or sentence can be represented as a vector, like AI has been represented as a vector here, and is also has been represented as a vector, and fun has been represented as a vector. So when we combine basically many words, we can get a matrix of word embeddings, right? So together they form a kind of a 3x3 matrix with that models basically a sentence, like AI is fun, like it models a complete sentence here, you can see here, right? The third and one of the most basic examples which we will learn in other lecture series is about neural networks. So we can represent neural networks as a matrix operation. Each layer is a neural network and is basically operated by this very particular basic equation where X is the input matrix, like it can be here, like the embedding matrix that we have. W is the weight matrix, which is regularly updated. As we learn neural network algorithm, we will understand the importance of weights, and Y is basically the output, right? And B is the base. This is also a matrix, column matrix, you can say, right? So this is the motivation of learning behind matrices. Uh, Basically, matrices are the backbone of every AI model. They turn like raw data into intelligence that you have, right? So let's first define matrices. What are matrices, right? We go down here. So matrix we can define then is basically a rectangular representation of numbers, like in this form Aij, right? Uh, or which consists of either real number or complex number, right? These are known as the columns, right? If we can zoom in here, these are known as the columns and these are known as the rows, right? So now if we look into the details of the matrix, like let's say for example when I say that it's a rectangular representation of either real or complex, what do I mean? So let's say this can be a matrix AI 1, 0.2, 2, 3, right? And this can also be a matrix. Let's say B is equal to 1 plus I minus I, 2 and 0, right? This can be also a matrix. So this basically lies in the field of complex numbers, and this is from the field of real numbers, right? From here also, like if the matrix has got m rows and n columns, then the order of the matrix is defined as m cross n, right? Consequently, the number of elements in this matrix is let me get the eraser. Number of elements in this matrix will be m cross n. Like here it is 2 cross 2 matrix, so the number of elements is 2 cross 2 is equal to 4, right? Another important definition before we move into the area of understanding the different types of matrices and the types of operations that we can understand is the concept of fields, right? So a field is basically a set of numbers where we can add, subtract, multiply, and divide. Like these operations hold on fields. Basically, what do we need to understand here is that if I say that a set of numbers is a field, then these operations are proved on that particular set. So let's say, for example, I consider the set of real numbers. What is a set of real number? Uh, it has these number 0 0.1, 0, 0.0001, and so on, infinite number. So if you consider the set of real numbers, if I say that if I take a number from a field of real number like a is equal to 1 and b is equal to 2, right? Then these laws, the law of associativity, the law of commutativity, the law of distributivity, the law of identity, and the law of inverses all hold on these numbers. What do we mean by the hold of these numbers? Like basically, if I perform like a simple operation like addition, like a plus b is equal to 3, which again lies in real number, right? If I subtract a minus b, which is minus 1, which again lies in real number. If I divide a by b, which is again 1 by 2 is equal to 0.5, again lies in real number. So any operation that you perform in the set of real number, the result always goes back to the real number, right? So that is what we mean by the term fields, which we will use throughout the learning of the matrices. Great. So now we will move to understand the type of matrices and the operations we can perform on the matrices. So we will start understanding the different types of matrices that we have here, and we'll first start off with the row matrix. The row matrix can be simply defined as the one having a single row but n columns, like single row but n columns. Something like an example could be a row matrix example a11, a12, and up to a1n, right? Example could be like 1 2 3, right? It's a row matrix, like it has a single row but 3 columns. It's also known as the row vector. Similarly, if you want to consider the column matrix can be defined as one having n rows but a single column, like n rows but a single column, something like this. Like it has got a11, a21 up to an1, right? An example again could be something like 5 6 7, right? This is a column matrix having 3 rows and a single column. It's also known as the column vector, right? Uh, the null matrix or the zero matrix is such that where each element is 0. It's also denoted by 0 m cross, sorry, this needs to be corrected here, 0 m cross n, something like let's say 0 0 0 0 0 0 0 0 0. It's a null matrix of the order 3 by 3, right? Okay. A diagonal matrix now. A diagonal matrix is where you have got only the diagonal elements. So something like this, right? It can be defined as that that for all aij that you have here, the matrix definition, aij is equal to 0 if I is not equal to j, right? Otherwise it's non-zero. Kind of example would be like 1 0 0 0 3 0 0 0 4, a diagonal matrix, right? A scalar matrix is one which is kind of like this, a multiple of the identity matrix. I. Here is the identity matrix. We'll first define that. Okay. So identity matrix or the unit matrix is defined as one where the diagonal elements are all 1, 0, 0, 1, 0, 0, 0, 1. Right? And similarly, the scalar matrix is one where k is any real number or scalar. So ki could be k 0 0 0 k 0 0 0 k. An example could be, let's say for example k is equal to 3, then the scalar matrix could be of the formation of if k is equal to 3, then we could consider this as a scalar matrix 3 0 0 0 3 0 0 0 3. Right. Now let's define upper triangular and lower triangular matrix. We are going through these matrices to understand in depth what are the different types of matrices, and in the later chapters of the matrices and determinants, you will observe that how upper triangle and lower triangular matrix plays a role, or unit matrix or diagonal matrix or zero matrix plays a role in different types of operations that we will see. Okay, so it an upper triangular matrix. And upper triangular matrix is a matrix if all entries below the main diagonal are 0. Now let's observe two options here. What is a main diagonal, right? So in a matrix, right, like, by the way, this is a square matrix for upper triangular matrix. So a12 a13, let's say for example a21 a22 a23 a31 a32 a33. So this is the main diagonal, right? So the upper triangular matrix is basically saying that entries below this diagonal element should be 0. That is, this and this should be 0. So an example could be, let's say for example, something like 1 2 5. Then again, like, let's say for example, this could be 0.3 5 again 2. This is again 0, this is again 0, and this could be something like 0.7 or something like this. So this is the upper diagonal, right? And below this are all 0. You can see that. So this is an upper triangular matrix here. Similarly, for the lower triangular matrix, anything above the upper diagonal should be 0. So you can observe this here. Right. So a similar example for lower triangular matrix, let's just remove this part here. We need to make way for us, and so here. So for lower triangular matrix, an example could be something like 1 0 0, then again 1 1 0 2 5 3. Right, so anything above the upper diagonal is 0. Right, so that's an example of a lower triangular matrix. Now let's understand few properties of addition of matrices before we go back to the types of matrices again, because this requires some intuition into other properties and or operations on matrices, right? So let's go ahead with that. So these are the properties for matrices for addition of matrices, right? So what do you mean by properties of addition of matrices? We mean that for a matrix A and B lying in the field of real numbers or complex numbers or any field that you have defined, right? Remember, we have already defined the field definition earlier. So a matrix A comma B lying in a field of real or complex number or any specified field that you have defined will satisfy these properties, like a plus b will be always equal to b plus a. It will always hold the law of associativity. Additive identity matrix it will hold, and additive inverse it will hold. Also it will hold the rule of transpose. We will understand basically the operation of transpose below, but keep this in mind, like at least so that we are good with at least the properties. Okay. Similarly, for properties of addition of multiplication of matrices, which is a very important function for matrices, uh, if A and B again belong to a field of real or complex numbers, like the commutative, the associative, the distributive, identitive, null matrix operation, and cancellation law and the transpose law holds good, right? Now the most important part of understanding the multiplication of matrices is, like, let's say for example there is a matrix called A is equal to 101, 101, 210, 1 2 3. This should be here, and again b is equal to, let me go this way, b is equal to, let's define that as 2 1 1 2 and 1 4. So what is the order of the matrix A? You can understand it's 3 by 3, and the order of matrix B is 3 rows and 2 columns. Now what will be the resulting matrix from here? The resulting matrix C is equal to AB will be 3 cross 2, and this is only possible when this is let's say for example this is row, this is columns, and this is again row, this is columns. When column of matrix A is equal to is equal to the number of rows of matrix B, then only the multiplication between two matrices is possible, otherwise it's not, right? So let's go ahead and observe that how we can multiply these two matrices, like A B is equal to, so the matrix multiplication, now let me erase this, let me get this a bit bigger. Matrix multiplication is by basically multiplying your rows to columns, like this row will be multiplied to this column, and again this row will be again multiplied to this column to form two elements. Let's do that. This is 1.2 plus 0.1 plus 1.1, and then again this is 1.1 plus 0.2 plus 1.4. This is again 2.2 plus 1.1 plus 0.1. This is 2.2 plus 1.2 plus 0.4, which is element wise multiplication. That's it. 1.2 plus 2.1 plus 3.1 plus 1.1 plus 2.2 plus 3.4. You just have a square matrix here. Let's go on. So the finally you have got here, what you have is 2 plus 1, 1 plus 4, 4 plus 1, 4 plus 2, 2 plus 2 plus 3 here, and this is 1, sorry, my bad, and then you have got 1 plus 4 plus 12. So this gives us 3, 5, 5, 6, and then 7, 17. So this is your resulting matrix, right? A few important points that we would like to talk about the multiplication of matrices is that it as I've already said this point, but let's define it in a more clear way. Like, let's say for example, if a is equal to of order m comma n, or let's define it this way, sorry, the most mathematical definition, like if A is a matrix of order m cross n, B is a matrix of order n cross p, then we have AB exists, right? Because n, right, which is order of C, let's say for example of order m comma p, but BA exists only if P is equal to M, meaning that BA is not possible, right, until and unless this is equal to this, right? The what do we mean by this? The implication is that AB is not equal to BA, right? Basically, the commutative law does not hold in matrices, right? Okay. So that was about properties of multiplication of matrices. Now let's try and understand transpose of a matrix. Let's remove this. We will now understand the transpose definition. What does transpose mean? Uh, So basically, in simple words, like if I want to put that the transpose of a matrix is basically formed by interchanging its rows and columns. Simple, right? So let's give it a formal definition here. Like if A is equal to Aij, this is just okay. If A is equal to Aij, then what will be the transpose be? So then A transpose is defined as, we can define as I over Ij is equal to Aj. Basically meaning that if you have a matrix called 2 1 0, and then you have 1 0 1, and then you have 1 1 2, then A transpose can be 2 1 0 1 0 1 and 1 1 2. Basically you interchange the rows and columns here. That's what transpose of a matrix means, right? So let's now understand the properties of transpose. Like first is the A transpose of transpose is A again. Obviously, like if you have a matrix like this, A transpose, and again if you perform transpose on this, like A transpose again a transpose, then that will result in again in the same matrix 2 1 0 1 0 1 and 0 1 2. By the way, A transpose is also represented as A dash, right? Okay. Again, this is again a k is a constant, k is a scalar. Like k of A transpose is equal to k A transpose. This is pretty much very obvious that let's say for example that if you have something like ka, like continuing with the same matrix from here, like if you have 3a, which is equal to basically 3a will be equal to 6 3 0 and then 3 0 3, and then that will be equal to 3 3 6, right? And again you have the ka transpose, like if you multiply by, let's say for example 3a transpose, so that will be again be equal to So yeah, uh, we'll just clear this out a bit to understand this in a better way. Where were we? So if it is 3a and if you take the transpose, it should be 630, and then it should be 303, and there should be 336, right, which is basically 3a transpose. Now if we consider a transpose, right, this is the a transpose, and multiply it by 3a transpose, which is basically this we have done. 3 transpose should be 633, again 303 and 036. So we can see here that both are equal. So yeah, this property also holds good. An example. Similarly, if we continue on our quest for understanding more properties of the transpose, like A plus B transpose is again equal to A transpose plus B transpose, which is pretty evident as it holds the law of additivity. Similarly, for A minus B transpose is equal to A transpose minus B transpose, and A n transpose is equal to A transpose n. What do we mean by this is basically that let's construct an eraser here. Let's try and understand this by a trivial solution. I will try and take a simple solution, simple example to understand this, and can then. So let's say, for example, you have A here defined as an identity matrix 1 0 0 1. So A square will be again 1 0 0 1. So if you take A square uh, transpose will be 1 0 0 1, right, and if you take A transpose and then square, which will again 1 0 0 1, which is pretty much equal, they are the same. So this property also holds, and it holds for almost all matrices. I think you can give it a try for a trivial matrix, like let's say consider like A is equal to 1 2 0 1. Try this out and let me know in the comments if this works or not. Okay. So the other is, I think we have missed a point here. It should be A transpose here. So trace of A is equal to trace of A transpose. What do you mean by first trace of A? Let's see what do we mean by trace of A. Trace of A. So trace of A is the sum of the diagonal elements of a matrix A. So let's say, for example, like if you have a matrix such as A is equal to 1 2 3 0 2 4 and 0 0 1, right, and if you consider the trace of A will be equal to 1 plus 2 3 3 plus 1 4, right, you are summing the diagonal elements, right, and let's say, for example, trace of A transpose. So let's say, for example, what will be the transpose of A? It will be 1 2 3, it will be 0 2 4, and it will be 0 0 1. Again, similarly, like if you consider the trace of A transpose, it will be 1 plus 2 3 plus 1 4, which is pretty evident here, right? So it's same. Okay, now the second part, or the most important part, for which I have already defined the definition of fields, is the conjugate of a matrix. Like, what is conjugate of a number? If you can define that, then you are pretty much close to understanding what is conjugate of a matrix. So let's understand that what is a conjugate of a number, or a complex number, to be very specific, right? What is a conjugate of a complex number? Like if you have studied complex number, they are in the form of A plus IB. What is Like if you have studied complex numbers, you are pretty much evident with the definition of a plus ib, right? Right, where a and b are in the field of real numbers, right? So what is conjugate of a complex number? So the conjugate of a complex number is reflection of a number about the real axis. So let's say, for example, if you have this, right, uh, and then c is equal to a plus ib, then c bar is equal to a minus ib. That is basically the conjugate of a complex number. This is x-axis, this is x prime, this is y, and this is y prime, right? Now what is conjugate? Then what is conjugate of a matrix? Now the a matrix A, right, of order m comma n, then the conjugate of A is basically A bar, right? So basically if A bar is denoted by Aij bar m comma n. Now let's say, for example, if I define matrix A as 1 1 plus I, and then 2 plus I. So what will be the conjugate of matrix A? It will be A, this is 1 1 minus I, 2 minus I. That's it. So that is the conjugate of a matrix, and these properties hold very well. Like conjugate of a matrix is equal to the matrix itself. Like if you take basically if you have A bar, and then you have, I think this will be A bar bar, so A bar bar, right? And so again, like if you take here, so the same matrix A bar bar, it should be 1 1 plus I here, then again I, and then 2 plus I, the same thing, right? Let me just clear this a bit. So you have got this, then you have got the basically the conjugate. Okay, so this is basically, this should be this, right? Then you have got the multiplication conjugacy property and the transpose conjugacy property. Similarly for real number, for the complex number, and for the invertible matrices. These properties will be applied, and we just need to remember this and understand them well. Now let's move on to the part of understanding types of matrices again, as we know now what is a transpose of a matrix. Now the first matrix that comes to the picture after understanding the transpose of a matrix is basically symmetric and skew symmetric matrices. What do we mean by symmetric and skew symmetric matrix? Symmetric matrix is a matrix in which A transpose is equal to A. So let's say, for example, an example could be like 1 0 0 0 1 0 0 0 1. It's a trivial case, but it's just for the sake. Like, so if you take A transpose is again 1 0 0 0 1 0 0 0 1, which is equal to A is equal to A transpose, right? If you consider this matrix also, like in the example, like if you have this matrix A, then if you consider A transpose of this matrix, it will be 1 1 minus 1, and again it will be 1 2 0, and then it will be minus 1 0 5, right? So which is again equal to the matrix itself, like A transpose. And the skew symmetric matrix is where A transpose is equal to minus of A. Like basically, like if you consider, like if this is the matrix, right, and if you consider the transpose of this matrix 0 1 minus 2, and then minus 1 0 3, and then 2 minus 3 0, right? And if you multiply it by -1, let's say for example this is a scalar quantity here, -1, it will be 0 1 -2, it will be -1 0 -3, and it will be 2 -3 0, so which is equal to the matrix A itself. So that is a skew symmetric matrix here, right? The next matrix that comes to the picture is an idempotent matrix. The idempotency is basically defined if A is a n cross n matrix, and then you have got A square is equal to A. Now here identity matrix and basically the null matrix are trivial examples. So let me just do one trick here, not a trick, basically a proof here. What do we mean by if I say that identity matrix and the null matrix are basically trivial examples? What do we mean by that? So let's try and understand this a bit. So A square is equal to A if you have A square minus A is equal to 0, which is basically a null matrix. And if I take A here, then you have got A minus I is equal to 0, which means either A is equal to 0 or A is equal to I. These are trivial examples. 0 is the null matrix, I is the identity matrix. On the other side, we can take something like this also, right? A square is equal to I. We know that, right? So if A is idempotent, then basically A minus I is also idempotent. Like if A is idempotent, which means if A is idempotent, which means A square is equal to A, then I is also, like basically I minus A is also idempotent. So if A square is equal to I, right, which implies A minus I, A plus I is equal to 0, or I minus A or I plus A is equal to 0, which implies that I minus A is idempotent, as basically if you can see that I minus A is equal to null matrix, so I is basically to A. So that's also one of the areas, or basically one of the results that we can derive from here. Okay, now we come to one of the most important matrices as a result of transpose is the orthogonal matrix. The orthogonal matrix is basically, it says that if A is an orthogonal matrix, then A transpose or A transpose A is equal to the identity matrix. It's pretty evident from here. Like if you consider A matrix and the A transpose matrix is cos theta minus sin theta, then A transpose A is equal to I. This will be, if you go deeper into the mathematics part of linear algebra, this result is used to derive a lot of theorems. So this result will be used in further study of our machine learning part also. So yeah, now as a result of the conjugate of a matrix that we have understood, we'll just try and understand the conjugate transpose also. It's the same thing that we have followed for the transpose of a matrix. The pretty much the properties are all the same here, right? So yeah, A plus B transpose, and all other results are the same, but we will need to focus on the part of this matrix here, an important type of matrix, which is the Hermitian matrix and the skew Hermitian matrix. So let's understand that. What is a Hermitian matrix? A Hermitian matrix is a matrix if it is equal to its conjugate transpose matrix. By the way, it's a square matrix, right? So what do we mean by that? So if A is equal to 1 plus, sorry, this is A 4 minus 5i, 4 plus 5i, 5. If it is Hermitian matrix, then A is equal to A theta, right? So what do we mean by conjugate transpose of a matrix? Conjugate transpose, conjugate and then a transpose. So let's apply the conjugacy here first. What do we, so already I have said that the conjugacy means that if I apply a conjugacy, it will be 1 4 plus 5i, 4 minus 5i, and this will be 5, right? Now it says conjugate transpose, so conjugate and then a transpose. So 1, this will be 4 plus 5i, this is 4 minus 5i, and 5, which is equal to the matrix A, which actually shows that it's a Hermitian matrix, right? Similarly for skew Hermitian matrix, right? The skew Hermitian matrix holds the same as that we have seen here, the skew matrix, the skew symmetric matrix, sorry, my bad, right? So it's again equal to, if A is equal to minus A of conjugate transpose of a matrix, right? I would request you guys to just try this out to see if this is a skew Hermitian matrix or not, and maybe comment out that if it works out or not, right? Okay, so with this we end the types of matrices and the properties of matrices. If comment and tell me that if there is any part of matrices which you couldn't grab, or if I would be required to go through it again, or any part of a matrix which I need to focus much more on, it would be very helpful. If you found this video very helpful and useful for you, please like and subscribe. Thank you.